Where did the quiz go?
All right, who can tell me what
Just randomly grab it.
Boyle's
I thought you
law
put it in there.
formula was? Because you should, now there was no quiz to study for, so you actually should have looked over your gas law notes.
F1 times
I'm hearing
V1.
Julia say P1, P1, P2, P2.
Oh.
Yep.
Sure.
PB,
He spilled the entire soda.
No, we did not. The entire soda is still in the thing.
Very nicely done.
I would exaggerate it.
Can somebody give me Charles' law?
V1,
Cups.
V2, V1, V2.
Paul Rivers back.
That's right. That's right.
And again, you might see it like this. In fact, you will see it like this in your textbooks. Again, these are the same formula. And I would definitely,
Oliver.
I saw it.
I would definitely go with this one. It is a better chance that you'll make less algebraic errors. Just make sure we label everything correctly.
I got a 53. Where'd you get it?
Okay? That was yesterday.
Look at the line.
I have 68.
No, you did not. No. No.
And
Oh yeah, we don't like cross multiplying. Or we don't like.
we should,
It was a
I'm
72.
hoping,
You keep changing your answer.
we should be able to
Either
wrap up
72 or 68.
our gas law
Yeah,
lecture,
whatever it is,
which
it's
will give
true,
you,
one of
the
those
reason I
is
really,
Both of those are.
try this again.
You're just mad because I did better than you.
How'd you gain 72 in chemistry?
The reason I would really like to do that is that it gives you multiple days then to study the entire, that looks much more pretty.
What's today's date?
The funny thing is, I did good on the back end, but the multiple choice I didn't hear the wall.
I did the opposite. I got 68 points on the first page. I also got my name right. That's a free 30 points.
Yeah, so you're lying, so. Show me it then. Show me it
I
then.
already crumbled it up.
It's in your pocket.
No, it's not. This pocket?
That.
This pocket is empty.
Where'd you put it?
This pocket. I'm not telling you.
And all of our temperatures must be in Kelvin. Are we ready?
It's already filming.
Oh, we've been filming. Excellent. Nothing like a little bit of filler.
Yeah,
It drags out the ad revenue, so.
Definitely, I know we're racking in that ad
Yep.
revenue.
You know it.
We're getting sponsored by Raid Shadow Legends this month, guys.
Famous, I don't think is the word.
How's it already have gone?
There might be some people checking it out. We'll go to examples later.
Wasn't it quarterly?
All right. These are the two laws we have done already. Whoa, shoot. Of course, you can hold some other things constant and look at how that works. Amaton's or Gay-Lussac's law, again, both of them kind of done the, you can handle that, you can handle
Yeah,
it.
but the most.
It's on
They
video.
both kind of were writing papers at the same time, delivering their results, and so they both kind of get credit, actually.
How do you say
I
the
think
second
it's,
one?
Amaton is actually the one I think that actually had it first, but Gay-Lussac is the one who gets credit for it, or had credit for it for a longer time. Again, they're dead people now, and so it really doesn't matter.
Oh.
It's not like they're taking offense to it.
You don't think they're looking?
But since it is directly
These guys are looking
related,
up some help, let me just say. They created this.
no need for side conversation. Since it is directly related, then we would hopefully think that it should look a lot like Charles law, and it does.
Let's see.
And of course, in textbooks, you will see it in the quotient form. And again, I would definitely use the one without denominators in order to make your algebra easier. Again, directly related. That's a, those inversely and directly are ways for you to check your work. For instance, if you do a volume and pressure calculation and one doesn't go up and one doesn't go down, then your Boyle's law, you've obviously put the numbers in wrong. It should be inversely related. Again, this should really be the only new note right here. All the other notes you have already. So last lecture we had 3 formulas we were supposed to know. Heat of vape, heat of fusion, and then the Q equals mass times C times delta T. This one we, of course, have now 3 gas laws. Remember, these are laws of nature. These are behaviors of gases that the kinetic molecular theory tries to explain. Again, tries to explain. Now, of course, you can put them all together. Let's go backwards. And technically, I think you guys can kind of figure this out. If you were to really stick all of these things together, notice we have volume, temperature, and pressure all here. Who believes they can probably figure this out? Well, I could stick all of these variables together if the amount of gas is held the same. It's all right.
Would you add them or no?
We don't.
Would you
don't
just
Or
add
just
them.
squish
add a
together?
T1 to T2 to the Boyle's? First
Yeah, you could do that. That's a good way to do it because, and if we take Boyle's law and just divide it by T, it's kind of a combined of all of them. Or we don't want to do the division by T. We'll do it so we can have no denominator. So yes, you can combine these if the amount N is held the same. And it's called the combined gas law.
So funny.
Now, is it technically a
what
new
he said.
formula?
No.
Oh.
Not really, because here it is,
That's
V1
on
times
there,
V1 times
just gotta keep on.
T2 is equal to P2 times V2 times T1. And again, that is holding N as constant. And believe it or not, that is a normal kind of situation. For instance, if you have an amount of gas and you want to see what the pressure, temperature, and volume manipulations do to it, you won't change the amount of gas. I mean, we can easily do a quick demo now.
Demo time?
Kind of. I'll call this the Jeremiah demo.
What?
no correlation.
So notice what I will do. I will take this balloon.
Can you make your voice like super squeaky?
That's with helium.
You ain't retarded.
There you go.
I don't know if I should
Oh, I know.
flatter.
It's like, can you?
Yes, sir.
Got pop. It's gonna be so funny.
It's about to pop.
It's not gonna pop.
This is.
Please pop.
All right. So
That's like impressive.
I now have this balloon, and it won't take too much of a effort. Here, hold said balloon. Please don't pop.
Somehow it's gonna pop.
For our viewers.
Just a blue screen.
Balloon.
Balloon go bye bye.
Nicely
No.
done. Nicely done. Way
did
to
it.
almost hold the balloon.
Oh, I know.
I always
So I will quickly take a
I don't just know science.
measuring tape, and this won't give me a volume, but it'll give me an idea of the volume of the gas. Oh, look at that. A perfect 34 inches
Show the
around this
screen.
area. I
it is. It's
think we're okay. 34, like right on the nose. That's nice. All right.
34 inches.
Excellent.
34.0.
Pop it.
True that, because it was right on the
If you
nose.
pop it, it'll change
No,
the shape.
now I will just take this
Do you know that?
beautiful chair.
Wait, no, we gotta bring the phone. Bring the phone, bring the phone.
Let the phone, let the phone.
Oh, cameraman. Why is this experiment even ever?
I don't know.
Because you
Say hi, class.
you were the one who figured out
What am I
Steady,
filming?
They gotta see the lab.
that my
He's just getting
soccer ball
taped.
deflated
I'm
It's
so
very
smart.
important.
Oh my gosh.
outside.
Why are you doing it through the glass?
Alright.
I'm not.
Which isn't really Jeremiah's law, though. It would be
It has
Charles'
to be his
law.
last name. That's why.
Abandoned go-kart
And a Bogart's law.
Abandoned go-kart law.
So, what are we not changing? We're not changing the pressure because atmospheric pressure is the same inside and outside the house.
First
virtually.
video where we moved.
Find out. We're not changing the amount of gas. The gas is trapped inside of the balloon. So we are changing the temperature because it is much cooler outside than it is inside. And so we will just give it a little bit of time and see what takes place. Dalton's law of partial pressure. This is an easy one, but because it is a sum, you're just adding, it's a summation. Yeah, gases are crazy. Who said so many rules?
Me. I said laws.
Yeah, so many laws.
Wow.
Dalton's law of partial pressure says that if you add up all of the partial pressures in a gas mixture, you get the total pressure. Okay, that's not a hard concept, I don't think. It states the sum of all the partial pressures of a gas mixture is equal to the total pressure. All right, that's not, again, concept, I don't think it's too tough.
Shout out Spring. Shout out Spring.
You should open it while it's on the phone.
After you are done writing that note, can somebody tell me what the formula would look like? Dalton's law of partial pressure states that the sum of the partial pressure of all the components of a gas mixture is equal to the total pressure of the mixture. So we got equal to the total. I got that. Total equals what?
P1 and P2.
P1.
And P2.
I like it. Very good. Whatever the first gas is, add that to the second gas. Add that to the third gas. Dot, dot, dot. Depending on how many gases are in the mixture. Very good, Rocky. Brain is in use. I love it.
My brain is
Yeah.
useless.
Our brains.
I wonder what the people think if they watch this about the side comments that these guys say.
There's been some scary ones. This is no longer YouTube Kids.
There's no YouTube kids.
I swear, I could barely get through it. Like, all I heard was y'all majority of the time.
I don't know what y'all talking
And
about.
who knows what y'all were talking about.
That will probably be
I turned the
After
volume
today's
down
video,
to
Oliver
closed
definitely got us
captions.
Bradley's full
demonetized.
comments, Oliver in the background.
Shout out,
Brain
Yay.
doesn't work at all.
Get a lot of that one.
All right. For instance, the total atmospheric pressure is virtually the sum of two main gases. Who remembers what the two main gases are in our atmosphere?
Hydrogen and oxygen.
Okay, I'm gonna go with oxygen because oxygen we know, but that's not the.
I learned a lot about pressure.
Glad it's not hydrogen.
Oh, no, it's not hydrogen.
Because we've seen hydrogen blow up.
Pretty crazy. Can we see, like,
Hindenburg.
We need to get on video.
Carbon dioxide is a very trace component in our environment.
hey, just
So,
want to point out
the
that
main
90%
two
of
that
the
makes up
viewers
over
are not subscribed. Make sure
98%
you hit
of our
that
atmosphere
subscribe
are
up.
nitrogen, which makes up the most, 78 to 80%, and oxygen, which makes up the other 18 to 20%. Now, yes, there's water vapor, yes, there is some carbon dioxide, no doubt. But those are all really trace gases compared to oxygen, and of course the major one, which is nitrogen. And of course, if you add all of those things up in our atmosphere, you get the total pressure of the atmosphere. So that's not, again, concept-wise, not hard. The math is not hard, but I will say this. Because it's a sum, that means percents. You can use percents a lot. In fact, I just use percents to do the atmosphere. 78% nitrogen. 19% oxygen. Because you can, and you guys sometimes like percents and sometimes don't like percents. So, and that brings us to the last of our gas laws. You already have that. Don't need that. And we're going to do a bunch of examples. And that is one that's kind of interesting. It's called the ideal gas law.
Is this one you said there's examples with?
No, we're going to do examples for everything.
Okay.
In fact, we get to spend the last little bit of this doing examples.
what? No demo?
And that should not leave you with a whole lot of homework or at homework.
Wouldn't do it anyway.
Because your Thursday is to be doing at-home problems. All right, ideal gas law. First of all, what does the word ideal actually mean?
Ideal. Point.
What happened?
It is the top of the line. Ideally, when I give you a quiz, I would love for all of you to get 100s on the quiz. Honestly, really, yes, that would be awesome.
He said he wants
Not only
to,
that-
wants me to
Yeah, he's lying to us.
And here, I can even go for not only does that demonstrate learning, and I would be very thrilled, but in a very selfish way, how easy is that to grade when everyone is getting all the right answers? That's really easy.
So we gotta.
So you would
be
save
Jack.
me a lot of time. Like I was trying to figure out there were like 2 or 3 papers that had a weird number on them that reoccurred, and I didn't know where the number came from. I usually could figure it out, but when it appeared on multiple papers, I was like, where is this number coming from?
Isn't
was
that the
it?
500 one?
Yes.
Yeah.
Oh, I got that.
523. I know, some people got it. Like,
Yeah.
a lot of people. I'm like, where are you getting? I put all the numbers together in many different combinations, and I
Oh,
could not
use
figure it out.
Get a
We're
live.
pretty good at what we do.
Yes.
I have an idea.
And that multiple people were sharing the same brain.
I have an idea.
It was
We all
very
share
odd.
brains now.
Anyway,
You should let the stream be like a
Surely.
live reaction.
That's
to
cheating.
this
That's
thing.
cheating.
I don't think so.
Cheating.
Um,
Share check. Just combine.
If it's not the right answer, I don't.
It is the optimal, it is the top of the line, it is this. Now, here's what I want to tell you. No gas actually acts as an ideal gas.
No gas means no car work.
But what we find out,
Thanks, Ron.
we actually can combine all four variables in one equation. And I know people are like, what? Some people are. How would you be able to do that?
I wonder.
I'll tell you.
He better.
Show messengers.
It is a very interesting equation, for
Shout out
sure.
Sprite.
And remember, we observe these. These are gas laws. So in other words, these things just happen in nature. When you change the temperature, the volume goes down.
Just watch these.
Like, it's very interesting how these gases behave. So what they found out is as they started manipulating these four variables, all of them, they would change the amount, they would do this, they started being able to predict things, but in order to predict them, they needed to put in a proportionality constant. So, you guys are pretty good. This is one thing I actually am finding that you guys really don't mind doing, and it started to click. You didn't like doing it at the beginning of the year at all. And that was putting constants or numbers in your brain. When I said, hey, go home and memorize that 4.184 joules equals a calorie, you all were in revolt for about a month.
I'm still.
I rolled the first one.
Yeah, I'm still.
That 101,325 pascals was equal to an ATM, which was equal to 760 millimeters of mercury. You guys did not want to do that.
I still have that though.
But now that I've been giving you things like, hey, the specific heat capacity of water is 4.184 joules per grams times degree Celsius. I saw pretty much almost on every paper, I wouldn't say 100%, but almost every paper, I saw that number on the paper. I'm like, hey,
Oh, that's good.
they're memorizing numbers that actually matter.
Numbers or letters?
Both.
Okay.
A little bit of both.
So, this is the gas proportionality constant, and notice these units. Woo! The gas,
Degree Kelvin?
yeah.
What the freak?
Bro, my pen.
The gas proportionality constant is R, is its symbol. And we're gonna memorize two of them.
As soon as I feel
My pen is just.
This one, notice the units are ATM liters and moles in Kelvin. So,
Okay. Wait.
That's scary.
Oh my goodness. Those God.
It's so scary. What is the least?
and then
My pen is.
we're gonna do one that has the SI units in there. These are the same number.
Yes.
I know they don't look like the same number.
I passed it. I know passed.
There is a lot of talking in the classroom. I know they don't look like the same number. Numerically, they aren't, but for value, they are. The only difference is the units for pressure and for volume. The reason I gave you the 8.314 is because these are actually, this is the SI unit. So if we were asked for the SI units, you would hopefully want to get everything into pascals and meters cubed over mole K. Now, are there other gas proportionality constants? Yes.
Who's Pam?
You change any one of the units, and of course you'll have a different constant. Of course you can have, instead of pressure in ATMs and pascals, you can have millimeters of mercury, and that would change the gas proportionality constant. Instead of for liters and meters cubed, you could have things like milliliters and decimeters cubed. So of course, that would change the gas proportionality constant. But these are the ones we will be strictly using in this class. So what is the ideal gas law? Does anyone by chance, because this is actually a very famous formula.
E equals MC squared.
Where's Jack when do we
Not
need
that
him?
famous.
A squared plus B squared equals C
Well, you know it's
squared.
going to put them all
Put that
together.
right there.
I know.
I'm just Pythagoras thing.
B
Hey,
equals square
You
root
said-
of
so you guys must be learning Pythagorean theorem because somebody on their quiz actually just used the Pythagorean theorem.
No
Hey,
way.
at least they showed some learning.
So someone in geometry used
Was
it.
it? No. It was on mine.
Yeah, but someone that's in geometry.
It just helped me like, oh yeah.
We would never use the Pythagoras theorem again. We left that in the past. We've been talking about it. Guys.
I use this.
A squared plus B squared equals C squared.
Yeah. Dumb.
Give me another room, my dude.
Notice, you do not need a change of anything to calculate anything here.
Yo, maybe you should have had this whole sprite. It's like you look like you peed yourself.
And again, to make these calculations,
I'll repeat himself.
please make sure that your temperatures are all in the Kelvin scale. So all of those things we did at the beginning of the year with ATMs, millimeters of mercury, joules and calories, all those things we did with converting Celsius to Kelvin, all of those things are all now coming back. And I told you they would. It's almost like I've taught the class before.
Hey guys, 90% of you viewers are actually subscribed, so
Hundreds of
if you
times.
guys could subscribe, that'd be great.
Wipe that.
It's really easy for you guys, and it just helps out the channel a ton.
I just absolutely
So yeah, please
I don't know.
subscribe.
Let me see the cat.
Oh?
Are we still recording this?
Yeah, we just touched when you're
We'll get some examples.
I
Yeah,
learned a lot
yeah,
about pressure.
Are we doing a
my
demo?
Sprite this morning.
yeah. You did what?
I learned a lot about pressure when I opened my Sprite this morning.
The sprite's now gone.
At least I can pee my pants.
Nice. Wait, Lesiak, are we doing a demo?
Well, we're in the middle of one right now.
Oh.
Can I use the bathroom?
No, cameramen don't get bathroom breaks.
Can I use the bathroom?
Okay, but we find out the least out of every table, so it's
Can I use the bathroom?
Yeah, camera. Well, you
Said it first.
Why is, wait, why does he? Oh, hold on. Bring the camera. Bring the camera. Go, 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 go.
Still rather large. It's been out long enough, I think. Aha! What does it say?
33.
33.
Top off the job.
Why do you? Oh my gosh.
Oliver, turn around. Turn around.
How is that even possible?
I already got it on video.
It's literally all. It's like all over.
I got it on video.
Silence you, silence. So, just by sitting it outside, we did lose an inch, but I do have some compressed air, which is can be very, very cold as it releases pressure.
Can I?
Whoa. This is our best video we filmed yet.
I know.
We had Oliver peeing.
It's shrinking.
That's the second time you dropped it.
I didn't drop it.
I'm losing my compressed air, and it's freezing my hand off.
Oh no, is your hand okay?
You know what that is?
Let's see if I got it.
You know what the mouse stop is?
from 33. No, I did not. Because I can't get it to come out fast.
It did shrink for the record.
You got this, Lesniak.
You gotta watch the video when we get home.
That's
I think we
beautiful.
can do this.
It's a work of art.
Yup, 30 minutes long. Dude.
It's only been 30 minutes.
Oh.
Oh. Dude, is this new tech?
Subscribe if you want to see more of this.
Like and subscribe in the next 5 seconds or else your house will blow up.
Subscribe right now.
Okay, we lost the YouTube Kids membership a while ago.
One's Jewish, the other one's awesome.
Got the propellant in there.
In this video over,
It's not going down. Can't get it to come out fast enough.
no longer YouTube Kids.
Let's go get stage right. This video is gonna watch it.
Yep. It's suicide again. Yeah. Oh wait, so he said 2. Because he thought the combined gas songs like that.
And then whenever the Sprite's filling, no.
Oh, show the video, show the class.
Oh, it's already on the video.
All right, he's all right. He had a little Sprite issue.
It's Sprite, everyone.
Because then he would not have to answer the question. He's going to go to the bathroom and answer it.
I don't know.
I should probably. Yes, Sophia. Yes, Sophia.
This video is wild. Can it go boom boom?
This video is gonna be so good, guys.
I know. This video might be cinema.
What's the brand of the air?
The brand of the air.
Yeah, the press air.
This blizzard is in your hand.
We got one more.
It is actually good enough.
Alright. I forgot they made League of Legends.
Alright, good. Alright, new compressor.
It's like when we did a
New compressor,
extra
new
credits
man,
thing,
so I like
one
this
of
hood.
One of my things popped. But it made it right.
Silence. Don't draw on yourself.
Hey,
I'm just redoing my tattoo.
that's still there?
We're getting some hairspray.
Are you a barber perchance? You seem pretty good.
I would use that, I
I
guess.
think he's a barber in his past lifetime.
He does look like he should be a barber.
Yeah, he's pretty good.
You be good at it? You're like a knife.
It's cold.
Could you do haircuts?
I would assume that it is. Big yo on it to shine.
Big yo on it.
This video is insane. What? Oh, he froze it.
Is it cold?
Now, notice the pressure inside this can has changed. Here. What's happened to this?
Wow, it's cold. Wait, can I spray it? Can I spray it?
Can I spray that cake down?
I can't get it to.
Spray that cake down.
I think I've made my balloon too big. In other words, I have way too much hot air. That was fun. Good. Thank you for laughing.
You're welcome. I'm not actually gonna watch this video.
Well, good. I didn't show Charles all. We didn't show Charles all great. We did see it go down when we put it outside. But in the sax law, we definitely, because as you, without depressing the trigger, do not depress the trigger.
Oh, the poor trigger's sad enough.
Container is changed.
Don't depress it.
Now, the amount of gas has also changed, so we got more of an ideal gas law situation going on there, but we definitely have seen the temperature decrease quite a bit. Always got to be somebody.
There's always got to be
All right, let's do some problems.
Pop it.
No. Loud noises can
that is
hurt
cool.
people's.
Oh, we missed it. No.
You guys see that on camera?
I told
Pop.
you.
That is
No.
great.
Was that? Oh, crap.
Mazel coming.
Ow, my hands hurt.
Can you give me that marker? Oliver, we got one video.
That was you. Wow, Sophia. I don't even have soda.
All right. Let's keep our gas releases to.
Sophia, come on.
All right, pick any number on any side.
6, 7.
You won.
Oh my god.
1. Let's go down the list.
3.
Oh.
Can we go board game shopping here?
3.
That was actually fun.
All
We
right,
do 1, put down the sheet.
we're good. We'll do number 6.
Remember when we made board games?
3.
Remember when we made board games?
We're gonna do more than one.
I do remember that.
The pressure remains constant. What will 42.3 milliliters of gas at 24 degrees Celsius occupy at? And it was cut off.
What?
My guess is that we'll just go ahead and say at standard temperature. I mean standard pressure.
Which one are we doing?
6. So just listen up. Just at standard pressure.
SP.
So write that in.
TB or SP? Wait.
At standard
What
pressure.
number?
6.
Hey,
All
so
right. Please notice it will be still number 6. At standard pressure.
It's not that hard, Charlotte, to get with the rhythm.
Now, actually, with this many people talking, it's very hard to pay attention. So why don't we all pay attention? I believe, it's up to you, I can't force you to do this. I do give you extra points if you show the 3-step problem solving method, but it can be very valuable in this section so that you can get your P1s and your T1s and all that other stuff straight. So for number 6, if I'm going in here, I can quickly, hopefully decipher. It says if the pressure remains constant, and I gave it standard pressure, so it's constant, what will the volume be of a gas at 24 degrees Celsius? So we're looking for the volume of a gas at 24 degrees Celsius. All right, let's see what we got. We have pressures constant. Standard pressure is 1 atm. And it's constant. Excellent. We have volume. No, we don't have volume. We have a temperature and a volume. Ooh, I get what it should be at STP. That's what it's asking. Standard pressure and temperature.
My 72.
Volume 1 in the problem is given at 42.3 milliliters. And at a temperature 24 degrees Celsius. And notice what volume will 42.3 milliliters of a gas at 24 degrees Celsius occupy at STP. So this temperature,
Number 6.
as I read the sentence, remember it's only one line, that temperature and that volume are linked. It says this volume at that temperature. So that's why I put 1 on both of them. Do you see that?
Aww.
Would we pick a lock to plug it in?
Well, we will in a second. Hopefully that will jump off the page. Now, we know that all of our temperatures have to be in Kelvin. So how would I get this temperature into Kelvin?
Multiply.
Do not multiply.
Divide.
Bradley.
Add.
Add what though?
No, now my paycheck's
Like-
gonna go down. Oh, it's got deducted.
180.
Listen up.
Zero cents to negative
Where did
1.
180 come from?
The Kelvin temperature
You owe him money.
is equal to the Celsius temperature and 273 degrees.
I was real close. That's just
I
about
said 180.
Now, when you get to college, there might be some decimal points there to deal with. I think it's 1-3,
down
but
by 100. Down by the bank.
But 273 will work, and that is what you guys are going to be. So we do need to add 273 to this to get our Kelvin temperature. And so that means the T1 is actually going to be
2 minutes.
297.
No, we didn't start filming right away, so probably glanced over.
Alright, so we definitely need to know this formula still. This is, again, a formula you learned at the beginning of the year. We have used it numerous times throughout this year. Just make sure we have that formula again and again. Alright, and then it wants to know the volume at STP. Well, we know the pressure remained constant. That's fine, so that we can say P2 if we want, but it's the same, it's 1 atm. We do now have a T2. Does anybody remember what standard temperature is?
72 degrees.
22.
So this note, which has also been in your notes already,
22 point.
no,
What?
It's 22.2.
Not liters.
What?
What?
standard temperature and pressure is 0 degrees Celsius in 1 atm. So if we don't know that, you need to know that.
Oh, it's
But that again has been used in your notes multiple times. So we know that the T2 is 0 degrees Celsius, which we now know is going to be how many in Kelvin?
273.
Quite a lot.
All right, so we don't, again, pressure really doesn't change. It says that it's remained constant. And so now when I look at this, I have a T1, and I have a V1, and I have a T2.
You need a volume too.
And I am looking for volume. So after, notice, Junior is correct. After you've set this problem up, it jumps off the page exactly what you need. Well, I need a volume too. So what I'm really looking for is this V2. So now I know that this is V2. So what am I looking for? V2. If I'm doing temperatures and volumes, which law am I going to use?
The second guy.
Rocky is correct. This is going to be Charles' law.
Would you just like have the V as like an I'm trying to find B?
Yeah, I'm trying to find volume, but now we know it's volume 2 is what we're looking for.
Why did we cross out pressure?
No, the pressure is constant,
Oh.
They cancel out.
so we really don't need it.
Sorry.
But some of you would list it there, which is fine. I mean, technically, you could use the combined gas law here too. You're going to get the same answer. But Charles' law does jump off the page to me. And if I remember, again, I know them. It's your job to go home and get these in your brain.
Not really.
Yeah, there is.
That is Charles' law, and now I can just plug everything in appropriately.
Yeah, like new thing.
This part of the math should not be difficult if you just take your time. Some people in this classroom, for some reason, I don't know why, I've never said, okay, now hand in your papers, unless you're doodling on the paper. But
What? No.
you've been given all ample time. V1, put it in the right spot, 42.3 milliliters, times, well, I don't know my T2, yeah I do, times 273 Kelvin is equal to V2, oh, that's what I don't know. This is my unknown. A lot of you use the term X. And then last but not least is my T1. My T1 was 297K. And notice, this math, this is why I like to set it up this way. This math really is kind of easy. We just divide both sides by 297K.
It's just solving for X.
297K. We know that that cancels here.
Algebra just probably
297K. And look what happens to the unit Kelvin. They all have 3 significant digits, so when we get an answer, it should be in 3 significant digits.
They did.
And who has got my answer here?
38.9.
38.9 milliliters? Yeah, it is milliliters, that's what's left. Now, let's see if it makes sense. Because Charles' law says if one goes up, the other goes up. If one goes down, the other goes down. The temperature went down, so the volume should go down. Did it? Yes. Yes, it did. So that's always a good check.
What if it did? What did you say, like?
If it didn't, then you probably put the 2s and the 1s in the wrong spot. Sophia just asked a great question. What if you checked this and it didn't go down, it went up? That means you probably labeled something wrong because Charles' law does say they're directly related. The temperature went down, so the volume should go down. So that is always a good check.
So would it be V2 equals 38.9 milliliters is your final answer?
Correct.
Correct.
Collector.
Can we do some more?
Oh yeah, pick another number.
1.
3 on the same side.
Yeah. 3.
Yeah, it feels like it's.
All right.
We've been filming for 48 minutes.
A 8-liter sample of helium gas at standard pressure is allowed to expand to a new volume of 22 liters. If the temperature of the gas does not change, what is the new pressure of the gas exerted, expressed in ATMs? All right.
That's Boyle's law.
Well, we're going to find out.
Wow. R.I.P. So,
I did 603.
36 green.
All right, off we go. No longer number 6. Number 3. It says I want the new pressure. So I want a new pressure, a pressure in ATM.
Diamonds are made under pressure.
Excellent. All right, let's get rolling. I have a first volume, 8.0 milliliters. At that volume, it's at standard pressure. So I have a pressure Does anybody remember what standard pressure is?
0. 1 ATM.
Yeah.
And remember, that's a perfect number, so this doesn't have significant digits.
This 3.
Standard pressure is 1 ATM.
What is he doing?
It's allowed to expand to a new volume. Uh-oh, got a new volume.
Crap.
What is the new volume? Liters. This was not milliliters, that was liters. And if the temperature of the gas does not change, what is the pressure in ATMs? Well, that's a new pressure.
What can
So I'm actually looking for P2.
And so
It's going to be left at ATMs.
P1, B1.
And so whoever said Boyle's Law, you were correct. Now keep in mind, this one's going to be inverse related. One went up, so the pressure better go down. We'll see if it does. P1, V1, 8.0 times 1. Remember, this is a perfect number. ATMs, liters, is equal to
I said it right.
2.0 liters times Rx.
Okay, look, Oliver. What I want you to do is look around the room. Just look.
Now the question is significant digits.
Three.
How many should I put my answer in
3,
according to what you
2,
see here?
3.
No, 3's not going to do it.
2.
0.
Remember, this is a perfect number, so that's got an infinite amount of significant digits.
2.
So
1.
8.0 is the one with the least. So this answer should have 2 significant digits. What is 8 divided by 22?
8 divided by 22.
6, 7.
Oh, it wouldn't
sounds-
be perfect. It would have to be.
What was it again?
No, probably really small. 1.0.
Push you back.
What point is it?
0.36
That's the
atmosphere.
minute alarm. 1 minute.
1 minute alarm. All right, so we've got
That was a
2
long
good
bus
examples
already.
in here. Here is your assignment. So listen, and this is good. It's on tape and video for moms and dads to hear too. You are to do your best on these. Like, set up as many of these as you can do. Get them done.
Get her done.
Best.
So we just like done with thermochemistry? Like not done, but like
The one thing I finally understand we're done with? Oh my god.
we have work on Friday.
The one thing I finally understand.
Wait, why would it